No, not why it's working.
What's worth proving more
We're
than once.
math types. We don't need to know why it's working. What I want to talk about though is a difference of mine. A few years ago, I used to run a course of incoming graduate students. Every July, we go for 5 weeks. 2 of us would be in the classroom 6 hours a day. The first couple of hours we'd be lecturing. The remaining 4 hours of the day, graduate students will be working on exercises that we set them. The informal title of the course was All the Math You Missed But Needed to Know for Graduate School. Formal title was Bridging the Gap Between Undergraduate and Graduate School. And the really informal title was Boot Camp. Brutal, yes, lots and lots of work. Every student came out knowing LaTeX inside out and able to present to the board. And also really good background in analysis, linear algebra, probability, a bit of complex analysis, some statistics, and analysis. Probably maybe things twice. But one of the things I used to tell the students in that rich course was if something is worth proving, it's worth proving in more than one way. Now, most high school students, many undergraduates, think that mathematics is this edifice of correctness. That there is one way of doing this, there is one way of doing that. There is one proof that is perfect. There is one answer, one way to get the answer, and if you don't find it, you're wrong. I learned in high school that that wasn't the case. I was doing a homework assignment, and it was finding the instantaneous center of motion of some body. And I did it. It was an easy problem, and went into class the next day, and my teacher had a wraparound chalkboard. And he presented the solution to the problems that he'd assigned in homework. And that particular problem, he took 4 times around the wraparound chalkboard to go through the details of computation. And I said, after he'd done this, Mr. Grassley, can't you just note that from this point to here and this point to here on the circle, they're both tangents, so they're the same length? And he was presenting the solution from the book that he was using in class. So the book didn't have this nice, easy solution either. That was the moment when I realized, yes, sometimes things can be done in different ways. You can get to comparable answers without having taken the same route together. And mathematics is a beautiful subject, partly because that happens all the time. Now, the incomparable Professor Kuykendall gave the first math club of the semester, and I gather that you proved that there are only countably many only countably many rational numbers, and that there are uncountably many real numbers. And I know you had thought ahead of time about maybe proving that there are infinitely many primes. So I thought I would focus on these 3 topics, mainly to show you up.
That's a low bar, baby.
So I gather you didn't do Cantor's original proof of the countability of natural numbers. You did a nice proof with different primes and experiments. That's what I saw today when I rewatched it.
Oh, that's, yeah, I used to show the fractionals.
So and so one of the geniuses of the 19th century, unappreciated during his lifetime, ridiculed by other mathematicians for the stuff he was saying didn't make sense until it did. That will not.
Yes.
Okay. I'll try and stick to these words then. So Cantor showed that you can list all rationals. Let's say the positive rational. And he showed that you can make a list of the positive rationals. Now, another way of saying this is that the rationals are countable. Listable and countable are basically the same thing. But I want us to focus on if you can list all the elements of a set with positive, non-negative integer subscripts, then that's the same thing as countable. And I don't want to get into the injections and bijections and surjections and other jections. I want to focus on this as how we think about calculus. So his proof, beautiful proof, is to consider the upper quadrant, right quadrant of the integer lattice. So just Z cross C, but only the positive part of it. And to identify the point A, B with the rational A over B. And then he said, well, we can take a diagonal walk through this lattice, going through these points in this order, and we can list them. So we're going to go this way, so this is 2, 1. And this is 1 over 2. This is 1 over 3. This is 2 over 2. And this is the wrong way around. And then 4 over 1, 3 over 2, 2 over 3, 4 over 4. And then one more, 5 over 1, 4 over 2, 3 over 3, 2 over 4, and 1 over 5, and so on. And we can list all of the lattice points in this upper quadrant. And then he says, but 2 over 2 is the same as 1 over 1. It's not in those terms. And 4 over 2 is the same as 2 over 1, and 3 over 3 is 1 over 1, and 2 over 4 is 1 over 2. So we'll cross all of those out and we'll shuffle everything down. Beautiful proof, right? And that is one listing. Of the set of all positive rationals. Now, I really like this listing, except I can't work with it. How do you compute it? Well, for small numbers, it's not hard. But we asked the question, what is the 10,000, sorry, the 10 to the 3,000th rational on this list? And I'm picking that as a big number, but not a particularly big number. We can certainly print out 10 to the 3,000 is one with 3,000 zeros after it. It's a few pages of text maybe, but not that big a number. And I maintain that this is likely to never be known. Because one of the things you have to do is figure out how many numbers you're subtracting off from this list. Which ones are you crossing out? How many of them? And if you go through and cross them out each individually, that's going to take 10 to the 3,000 steps, and that's not a very small number at all. And if you try and figure out how many you have to subtract off, even for each level, that involves factoring the sum of the numerator and denominator of that sequence. So here, the sum is 6. There are 4 numbers in between 1 and 5, which are not co-primed to, sorry, 3 numbers that are not co-primed to 6. So we have to cross out 3 numbers there. To do that, you have to factorize that sum. And when you're factoring numbers on this order, not usually going to have a good time of it. Now, quantum computing may change that. But we're still going to have to factor a huge number of numbers. And quantum computing won't help with that. Now, there may be some nice, clever analytic number theory that play a role, or nice, clever rewriting of clever sums over arithmetic functions. But I haven't seen a good way of doing it. And so I'm not hopeful that we'll ever know the answer to this question. For Cantor's list. Unfortunately, Jim, the list you gave last time, which you didn't even give, you just said it must exist. I don't think you can find the 10 to the 3,000th rational in that list either.
What list did I give?
You mapped A over B to essentially 2 to the A, 3 to the B for the rational.
Oh, yeah, good luck with that.
Yeah, yeah. So Jim actually asked for volunteers to list primes, and he handled all of the rationals, not just the positive rationals. And the primes that were chosen were, yeah, well, so I'll take your listing though and talk about it. So not the one you gave, but the equivalent. You can take A over B in lowest terms and map it to 2 to the A, 3 to the B, and you get a map from the positive rationals to the natural numbers, which I gather you don't allow 0 to be a natural number. I insist on it.
I put a little zero subscript.
Yeah.
Yeah.
I always say 0 is a natural number because for me, the natural numbers are the counting numbers. They count the sizes of sets. And my favorite set is the empty set. In fact, when Herb Wolf and I were putting together a journal, we mocked up a front page of the journal with multiple papers by various combinations of Herb Wolf and Neil Calkin and Herb Wolf, H. Wolf and N. Calkin. We had 6 different papers listed, and they were all something to do with subsets of the empty set. So those papers never got published, so this is just a mock-up of the journal. Okay, so this defines a function from A over B to the A, 3 to B. And it is the case that different fractions will have different representations as integers. And so now you can list the rationals can actually construct the listing of the rationals by saying we're going to walk along the rational numbers, walk along the natural numbers, and every time we see something that is an image of a positive rational under this function f, it will write that down as the next rational. So the rationals inherit the order from the image into the natural numbers. But now that we know the the rational numbers are countable, and here is a way of listing them, I would claim that we can actually get uncountably many different listings of the natural numbers. So not only can we find listings that work, we can find a huge number of them. Uncountably many, even though the rationals are countable. There are uncountably many different listings. Here's a proof. We will pick a transcendental number bigger than 1. And we'll map A over B to alpha to the A, 3 to the B. This is a real number. This is not a natural number. But this f is increasing in both the argument A and the argument B. The image of these will have order type so what do I mean by this? This is take all of the points that are mapped to by f alpha. And it will look like the rationals spread out on a line, the natural numbers spread out on a line. They will be real numbers, but they will be in an order that you can walk through. And then lastly, different alphas with different orders. And there are uncountably many alpha. So each choice will give a different listing of the natural numbers. So we've now got uncountably many different orderings of the natural numbers. Notice that in essence, we can make this into uncountably many different proofs that the rationals are countable. But it's much cleaner to have them to be countable in the first place and then this. Part of the reason for that is, how do we know the transcendentals are uncountable?
Because the algebraic numbers are countable.
Because the algebraic numbers are countable. And we really should have proved that before we said they're uncountably many transcendentals. But I maintain, you will never know the 10 to the 3,000th rational in any of these uncountably many orderings. And those of you who know me well, I will probably have told you the story that when I was an undergraduate, I had the option to take an optional computing for math majors class. It was all about writing backward Euler methods for solving differential equations. Halfway through, I decided it was optional. My favorite class to teach now, one of them, is the intermediate computation for math majors class here at Clemson, and we have at least one student here in the class, and it's scary enough a class that she's decided to come to this. So I don't know. I like being able to compute with math, and the fact that we can't get the 10 to the 3,000th rational in these lists is a little bit galling. So a few years after Herb, Wolf, and I started the Electronic Journal of Combinatorics, we finally wrote some papers together. One of which, a life lesson. We wrote a very nice paper on hyperbinary partitions of natural numbers. Beautiful paper. Submitted it to a decent journal, got back a lonely referee's report saying, oops, some of these results you already know. And after crying in our beer for a little bit, 6 months later, Herb wrote to me and said, you know, we've got that beautiful proof that the rationals are countable. And I said, yeah, and we can compute it. And so we wrote a paper for the monthly. And it's now one of my most cited papers. So I just heard Monday on Twitter, somebody tagged me saying, you know, Calkin, you'll like this beautiful paper. So I was writing that paper. So now I have to find a way of actually recovering from the fact that I've been gazumped. It was actually a paper related to what I'm about to say. So don't give up when somebody says that paper, nah. Make the paper better, find a different spotlight to shine on it, and it could become one of your most cited publications. So this should not be called what many people call it. I got an email from a student a few years later saying, I am pretty sure you've seen this already, but I found this really amusing. I had not seen it. I immediately bought myself a couple of copies of this shirt. It says the Calkin tree on it. I'm going to talk about the tree of all fractions, which is what we called it in the paper. That's what it should be called. We were not the first people to observe that this tree had nice properties. We just wrote a nice paper about the fact that it has this nice use. It was a well-written paper. We didn't claim it was new research. We claimed it was a nice result, not a new result. That's not accountable, that was done by Cantor. The tree of all fractions starts out like any good binary tree with the vertex of degree 2. And all the rest of the vertices have degree 3, hence binary. Every vertex has 2 children, hence binary. And we're going to label the vertices of the tree in the obvious way. And when I say the obvious way, I assume you're all seeing the pattern. I'm kidding. So vertex A over B has children A over A plus B and A plus B over B. So each vertex has a left child, which is the numerator over the sum of the numerator and denominator, and a right child, which is the sum of the numerator and denominator over the denominator. So if we look at a child, we can say, is it less than 1? Is it greater than 1? If it's less than 1, it's a left child. If it's greater than 1, it's a right child. And not only that, we can compute the parent's identity. So if we're given 7 over 3, we can see that that must be 3 plus 4 over 3. So it must come from 4 over 3. We can tell what the parent is. And notice that if A and B, if A over B is in lowest terms, that means they have no common divisor. Then A and A plus B have no common divisor, and A plus B and B have no common divisor. So a fraction in lowest terms has children in lowest terms. And so now we can give a proof that every fraction appears in this tree. Every positive rational number appears in this tree in lowest terms exactly once. I call this proof by very special technique. Here's what we're going to do. We're going to look at a fraction in the tree. Let's look at this one. And I'm going to say, you appear exactly once. How do I know that? Your mama appeared exactly once. This is a proof by your mama. Really a proof by induction. Right? Find the first level on which a fraction appears other than exactly once. Find that fraction and ask about its parent. Find a fraction that doesn't appear. Find the first one that doesn't appear on the tree. And its parent doesn't appear. So it's an earlier fraction. So it's really a proof by induction. But I like putting a proof by your mama. So now what we do is we read along the tree. And it turns out that if we write these down, we notice a pattern. And the pattern is that if we look at the denominator of a fraction in this list, and we look at the next fraction and its numerator, the fractions in this list are ratios of consecutive fractions where the fraction the terms are taken from a single list of integers. And this sequence satisfies a2n is an plus an minus 1, and a2n plus 1 is an. So I can compute a pair of consecutive fractions, sorry, a pair of consecutive terms in this sequence by computing a pair of consecutive terms further back in the sequence, halfway back. So it turns out that we have a very, very fast method for computing AA. Essentially, if you want to go out to the nth term, it takes log n calculations. If you go out to the 10 to the 3000th term, it takes 3000 log 2 computations, which is around 10,000 computations. My phone will do. So we can actually compute in seconds, microseconds, the 10 to the 3000th rational in this listing. And if we want to know where a particular fraction sits in this list, what its n is, what we do is we trace its path from the fraction through its parents back up to 1 over 1. And that will give us basically an indication of the binary representation of n. So we can go from n to a fraction, or from a fraction to n, incredibly efficient. So we can compute with this. It's lovely. You proved the reals are uncountable as well, right? Yeah. Did you change decimal notations? Did you
I
write down
did the
this?
counter diagonal.
And diagonalization. Beautiful proof, absolutely beautiful proof. I want to give you a couple of others. Why? If it's worth proving in more than one way. So Cantor's proof, Cantor's diagonalization proof was not his first proof. So what do we mean by uncountable? Can't be listed. Can't be listed. So if you give me a list of an infinite sequence of real numbers, I maintain there'll be a real number missing. And Professor Kuykendall said one way you can do it is you can write down the decimal expansion, change the nth digit, pick the nth digit of the Rn and tweak it and use those as the digits of a new number, and it will not be any number in that list. And it's a beautiful proof, fantastic proof. It generalizes to looking at power sets and changing a function from a set to its power set to show that you can construct a set that's not in the image. Beautiful idea. Cantor was way underappreciated. One of the problems with when Cantor was working is they were still trying to figure out what the heck the reals were. And how do we define them? What properties can we use in doing something like proving the reals are uncountable? So I would say these reals are distinct. Clearly, I don't get any more reals by repeating one, so I'm going to get rid of all repetitions. Makes things a little easier. We're going to construct a sequence of intervals. And they're going to be a decreasing sequence of intervals because each will contain the following one. This will be strict containing. So we're going to have A0 less than A1 less than A2 less than AN. And we'll have B0 bigger than B1, bigger than B2. So notice that the lower bounds are monotonic increasing and bounded above. The upper bounds are monotonic decreasing and bounded from below. So the A's and the B's tend to limits. And the way we're going to do this is we're going to walk along the list of reals and we'll say when we're at AN, IN. By the first two reals in the list which are in that interval, in the open interval. So, and then choose those to be the next AN plus 1, BN plus 1. We'll discard anything that doesn't fall into this interval. Now, if there are no such, then the interval doesn't have, it has at most one element of the reals in it, and there's lots more reals in that interval. So we must be able to find, if the reals were, if that was the countable list of everything, we would have to be able to find 2 more points in that interval. So we can always construct, either we can always construct a new interval, or we found reals that aren't on the list. So we might as well assume we can construct a sequence of intervals. Now, what happens if A infinity is not equal to B infinity? We've walked through, we've removed everything that lies between A infinity and B infinity. We've thrown everything out. So if A infinity is not equal to B infinity, that entire subinterval, open interval from A infinity to B infinity is not in our list. And we're done. On the other hand, if they're equal, we know that A infinity is bigger than everything in the list that's an AN, and it's less than everything in the list that's a BN, so it cannot have been an AN or a BN, so it's not in the list. Nice little proof. Roughly speaking, due to Cato. But part of the reason that it wasn't accepted is people didn't understand what the reals were. They didn't even know how to define the reals. Do we do it like Cauchy? Do we do it like Dedekind? Those are very different constructions. We need to show that they both work the same way. And mathematics, as a societal entity, was hell-bent on figuring out how to define the reals, let alone trying to figure out rigorously whether this is a good proof. Proofs are societal constructs. In order to be accepted, a proof has to be accepted by society. I want to give you another proof, which is, again, very, very short on completeness. So, given that same list of reals, so we're going to take our list, and for each real number Rn, I'm going to place an interval around it. The interval is going to be with, what do I want here? I want epsilon times 2 to the minus n minus 1, so these to be 2 to the n minus 2. So In has with length epsilon times 2 to the minus n over 2. And so the union of the ions has length less than or equal to epsilon over 2 times the sum n equals 0 to infinity 2 to the minus n, which is epsilon. Can you cover the entire real line with an interval of length at most epsilon? Or intervals with total length at most epsilon? No, you cannot. The real line has infinite length. We can only get covering an epsilon amount of it. Therefore, there must be bits that are not in this union. There must be a royal ton of reals that are not in this union. Okay, so we use measure theory to prove a result in number theory, in set theory. We okay, so enough about countability. Let's look at another infinite set which is clearly countable. This is a subset of the natural numbers. And this one, it doesn't matter whether 0 is a natural number or not, because we're going to look at the primes. We go to tensor. Right? I'm sorry, you go to tensor, is that right?
I don't remember what I did for this one, actually. No, I do. I think I actually,
No. I mean the time of this of MATLAB goes.
oh,
to
Tim
tensor.
Hill. Sorry, yes.
So there are infinitely many primes. Classic result due to Euclid. He said if there are finitely many consider the product of them, add 1 is divisible by a prime. By some prime q, not on the list. So this was incomplete. Contradiction, full stop. We couldn't have had a finite list of primes that covered all of them. Now that's a proof by contradiction which doesn't need to be a proof by contradiction. Because you can easily say, suppose we've constructed n primes, consider the product of them, add 1, let Pn plus 1 be the smallest prime dividing that value. There will be one, you could have proven that any number, at least 2, has a prime divisor. So you find the smallest prime divisor, call that Pn plus 1, and you construct an infinite list of primes. There are lots of ways of changing this. You could make this -1 so long as you start with 2 and 3. There's lots of open questions about which numbers are on these lists. Hard questions. And in the remaining couple of minutes, few minutes, I want to talk about different proofs of this. And unfortunately, MATLAB is not uncountable. In fact, it's not even infinite. So I won't be able to give you all 5 or 6 proofs that I really wanted to do. So I will mention, and if you want more details about this, ask Adam. Adam loves Furstenberg's topological proof that there are infinitely many primes. You set up a topology, and you take this topology and you say, if there are only finitely many primes, this set has to be open. but it can't be because it's a finite set and non-empty, and therefore it doesn't satisfy the rules. Beautiful proof, published when Furstenberg was an undergraduate. Such a shabby mathematician. No, first rate, very, very good mathematician. A lot of things that the interplay between topology and number theory, so it's fantastic. Okay, so I want to make sure I show you. So Euler, one of the most brilliant mathematicians ever to have lived, used unique factorization into primes for integers to show that if S is a real number bigger than 1, then the values of these two products will be the same. And essentially what you do is you say factor n into a product of prime powers, pick out the appropriate prime power from each of the terms here, there's only finitely many of them, and therefore you get a product which converges to the same thing. He then noted that as S goes to 1 from above, the harmonic series diverges, and so the limit of this, as S tends to 1 from above, must diverge. But if there are only finitely many primes, then this would be a finite product. And it couldn't diverge. There would be no trouble with it because each of the terms is non-zero. And it's a beautiful result. But what he didn't seem to observe is that you can actually make this much more quantitative. He knew that the divergence of this product of geometric series diverges if and only if this this diverges if and only if this diverges. And he knew that this diverges if and only if the sum of 1 upon p over all primes diverges. And then since the sum of 1 upon n log n, where the log n term is raised to a power bigger than 1, since that is a convergent series, Pn can't always be bigger than essentially n log n to the 1 plus epsilon. Now, the truth is that the prime number theorem says that Pn is asymptotic to something like n log n. That was conjectured a long time after Euler by Gauss, similar conjecture by Legendre. After Gauss conjectured it, it wasn't proven for 100 years until it was proven in 1896 by Villavalle-Poussin and Hallerau, independently, in the same year, 100 years after it was conjectured. This gets close. It is nothing like a proof of the prime number theorem, but it's close. And it's way better than anything you get from Euclid's proof that there are infinitely many primes, or Fermat's proof that there are infinitely many primes, or lots of other proofs that there are infinitely many primes. This is sort of the beginnings of analytic number theory. So a plug, there will be a course on analytic number theory probably next semester. Next semester does analytic.
Actually, I think that's right. It's Robert Dix, I think.
And we have a new faculty member who's an absolutely fantastic number theorist, and I will encourage you all to take his analytic number theory class.
The class is offering next semester.
Oh, algebraic number. Well, let this be a take his algebraic number theory class, and then
ask
a year later
questions about analytic number
analytic number
theory.
theory. Okay, that's all I wanted to say. Thank you for your attention.
Questions? Comments?
Anybody got a favorite proof of something that we didn't talk about today?
Pythagorean theorem.
Pythagorean theorem. Which proofs do you know? How many proofs do you know? Okay, that's not bad.
Wasn't one of them famously written by James Garfield?
Indeed, yes. I was going to ask them
And they
if
killed
they
him
knew
for it,
which president had his own proof of the Pythagorean theorem.
Yeah.
And not only did they kill him for it, but he would have lived if the surgeon who was poking around him to find a bullet thought to wash his fingers.
That's really.
And there was a metal detector in development that could have been used to locate the bullet. Lots of good stories about James Garfield. Wiki read on James Garfield. It's worth it.
Quadratic reciprocity. That's another one that has like a huge number of proofs in literature.
Yeah.
And that one's just miraculous fundamental theorem of calculus.
And it's another one where it was conjectured long before it was proven. So Euler and Legendre, I think, Euler for sure, worked out the law of quadratic reciprocity, which says when P is a square mod Q, when Q is a square mod P,
And how they're
P both prime, and how they're related. And the Legendre symbol was invented to make this a nice thing you could write down, but Euler had discovered the patterns much earlier. And it wasn't until Gauss, in the tender age of 17, I think. These just, no-name mathematicians. Gauss proved it and considered it one of the two things that was important enough that he felt he should reprove it and reprove it and reprove it. He gave, I think, 7 different proofs of that. And he gave several proofs of the fundamental theorem of algebra that every polynomial has a root. Every polynomial over R has a root over C. In fact, every polynomial over C has a root over C. Every polynomial of degree at least 1. Try and be precise. So Gauss was a big believer. It's worth proving. It's worth proving in more than one way.
I was planted here to remark that in computing, the same ideas apply, that if you have a problem you want to solve and you can construct multiple different algorithms for solving it, and proving that they are correct gives you different insights into the problem you're looking at.
And when he says he was planted, I told him to come here and make this talk. Thank you, man.
Okay, others?
So the one thing I do want to say